take 5 questions instead of 4 questions. And inshallah, we'll start with the first question, number 46. This is in chapter or belongs to chapter 12. Okay. So in chapter 12, number 46, we have this figure shows a cross section of a long, hollow, cylindrical conductor of inner radius. R1 is 3 centimeters, R2 is 5 centimeters. Okay. Let me show you what I mean by this hollow cylindrical. So I will go and show you the pictures. I think they are there. Okay. So it's like this one. Okay. So we have a conductor which is hollow from inside. So here there's nothing here. Oh, I can't write there. Okay. So there is nothing inside here, and all the current is moving on the skin, on the cladding, يعني outside, okay, the surface. طبعا هذا يحدث عادة يعني حتى في الطبيعي يعني في السلك الطبيعي when you are connecting things the current, sorry, it's AC. Usually it is moving on the surface. Okay, but this shape actually it's not something that you don't know. يعني الشكل هذا اللي تشوفوه أمامكم. This is actually in something called coaxial cable. You know that cable that you are using when you have the function generator, okay? And then you plug the cable to the oscilloscope. That cable actually we call it coaxial cable, okay? Which is made of 2 things. First is this one, surrounding cylindrical conductor like this one, and there is another one actually inside here. يعني هناك حاجتين داخل هذا الكيبل. One is the outer layer اللي هي هذه مثل الشكل الأصفر اللي تشوفوه أمامكم الحين, okay? And there is inner wire inside. The direction between these 2 cables are different, totally different. Okay, so one is going this way, the other one is going the other direction. And why is that in the coaxial cable? Because we want to eliminate the magnetic field outside. Okay, so this is actually, it has a practical use. يعني هذا السبب احنا ليش نستخدم الهولو, okay, الهولو conductor. Okay, بس الحين بعد ما بدينا بالproblem. Just this is general information about the cylindrical conductor of inner radius. R1 is 3 centimeters. So we know that this is 3 centimeters here. Okay. 3 centimeters. Okay. And here R2 is just 5 centimeters. Okay. 5 centimeters. The large circle there. And then we have a current, 50 amperes, distributed uniformly. Okay. Over the cross section flows into the page. Okay. So actually the direction of this cylindrical conductor, if you can see like that, okay, is actually going to that direction. Okay. So it's moving inside. Okay. So the current is going inside. Okay. So this is the story. So what is the question? Calculate the magnetic field B, okay, at R 2 centimeters. So that means less than 3 centimeters. And then this is the first situation, first case. Then the second case, R equal to 4 centimeters, which is in the middle between the 3 and the 5 centimeters. So this is the second situation. And then when R is larger than 6 centimeters, that means outside the conductor. Okay. So let's draw these 3 things together and then see how can we start with the first one here. Okay. So at the beginning here, we know that now this is the outside and this is the inner side. Okay. We know that this is 3 centimeters and this is 5 centimeters. But we have been asked to find the magnetic field from the origin here with a distance of 2 centimeters. Okay, so this is 2 centimeters. That means we need to know what is B here. Okay, so what is B here? So if I make a small loop here, okay, a small loop, because this point here, which is also far away with 2 centimeters, or maybe a point here, another point here, any point, okay, far away with the same distance from the origin. If I want to find B, okay, they should be the same. And usually, نعرف إنه when the magnetic field is a little bit have the same distance from the wire, so then we have the same magnetic field. But in this case, as you can see, if we can just add all of these magnetic field values together by introducing a small loop. So this is a loop. Okay? And this loop, actually, we call it Amperian's loop. Okay? So this is what we call it Amperian's. Who can call it also Amperian's law? Okay? So the Ampere's law, okay, let us to draw like a loop. This is like Gaussian surface. Do you remember Gaussian surface? That is surface, okay, 3D surface. But in our case now here, we have a loop, and that loop indicates all the B's, okay, that are with the same distance from the origin, okay. So what is Ampere's law actually, and why we need that one actually at the end of the day, okay? So Ampere's law is just right here. Ampere's law is just the integration or the summation of all of that B's of the magnetic field, okay, multiplied by that distance, small distance here, because when we have been asked B at this location, okay, we know if we can make this loop, this circumference of this circuit, okay, يعني هذا المحيط كامل, we can make it to small parts, يعني خلينا ناخذ أجزاء صغيرة. فالبارت اللي هنا بارت هنا راح نسميه دلتا ال او دلتا اس. Okay. Okay. فهنا we know that B is pointing to this direction. It should be يعني عادة. فلما يكون البي when B okay خلينا نكتبها هنا when B is parallel to delta L. ايش نسوي 3 lines. When B is just parallel to delta L, so in this case always theta equals to 0. So cosine 0 is 1. So no need actually to write it down there. And always these are parallel to each other because we have that circular loop. Ampere's, what is suggesting now here? Is suggesting that if you can sum up all of these magnetic fields that are far away from the same point, which is the origin now, this is what equals to a constant. And this constant is just the space permeability into the, okay, I enclosed. What is I enclosed? It is the current that is enclosed by the loop. Okay, so we should ask ourselves, is there any current inside that loop, inside the Amperian's loop? Okay, so this is the question. How many, what is the current first? Okay, and what is the direction of that current? Because that's very important for us. Do we have only one cable, 2 cables, 3 cables, and what is the direction of the current in these cables? Okay. Okay. So from the question now, we have been asked first of all to find the magnetic field B, okay, at R 2 centimeters. So this is why we draw our Amperian's loop inside here. Okay. And this is, as we always told you, this is imaginary. Okay. So the left side is imaginary. It's not real. Okay. So we should apply this to this one here now. But we know that actually B is constant. It should be the constant because they are apart from with the same distance. So B is out of the integral. It will be as a constant or uniform. DL is the small one. So the integral of DL actually, it is just DL here. It is just the path, okay, of the circumference of the circuit. Okay, equals to mu naught I enclosed. And we know this is just 2 by R, and R in this case is just 4 centimeters, which is 4 into 10 to minus 2 meter, okay, directly. Okay, and this is actually B. So this is just, we are putting the numbers directly. And instead of writing 2 by R, okay, and the summation of DL is 2 by R, okay? So this is the circumference of that small circuit here, okay? So this is now, we are speaking about that one here. Yeah. This will be equals to mu naught I. But unfortunately, I is what, Shabab? Is there any current inside that small circuit? Actually, there is nothing. So mu naught into 0. Why? Because I enclosed in this case equals to 0. There is no current here, okay? And because there is no current there, So in this case, B is what يا شباب? B is 0. Equals to 0 تسلم. Okay. Okay. So now we start to get and warm up by understanding how can we use Amperian's law like we used before the Gaussian surface or Gaussian law. Okay. So this is the first case, A. Let's call it A. When R equals to 2.0 centimeters. Okay. So this is the first thing. So now let's start and solve the second one, or second situation B. So let's draw again. Let's take another drawing here. Okay. So this is another drawing, and then I will change the color, make it green in this case. Now R is what, ya shabab? Now R is 4 centimeters. So we know that this is 3 centimeters, okay, and this is 5. Now we are not looking less than 3 or more than 5. We are looking in between 3 and 5, which is 4. So that means we are located actually here at this center here of the cylindrical conductor. Okay. So actually, this is now our Amperians. Okay. Amperes. Okay, loop. Amperians loop. So now this is the second situation where our Amperians loop now is located within the conductor. So now we should ask ourselves the question: what is the current that is enclosed by the Amperians loop? So this is the question. What is the current again? What is the current that is enclosed, that is contained? يعني ما هو التيار الذي يحويه هذا الأمبيرينز لوب الافتراضي اللي أنا رسمته؟ طيب ليش أنت رسمته هنا في المنطقة؟ لأنه هو سألني قال لي عند 4. Okay. So this is actually 4 centimeters apart from the origin. Okay. And we know they are دائما البي والدلتا ال. Okay. They are in parallel. Okay. في الحالة هذه. طيب. So left side is okay with me. So left side is okay. I know that this is the integral of P into dl equals to mu naught, okay, into I enclosed. This is easy to the left here. Why is that? Because we know B will be constant, and we know that this is 2 by R, as we said. R here actually, don't forget, at B, R equals to 4 centimeters. Okay? So don't forget that. Okay, mu naught is constant. We know it actually. It's 4 by 10 to minus 7. So that is constant. No problem with that. Okay. The idea now, how can we find I enclosed? Okay. How can we find this? Okay. Let's now concentrate here. There is a key point here in the question itself. The question said a 50 ampere current distributed uniformly over the cross-sectional flows. Oh, that means we have something called J, ya shabab. J is the current density. So the current density is the same through all the conductor. Okay. So it sounds to be like this is like a DC current. Okay? Because usually DC current is homogeneously or it is going with the same amount. So it's uniformly distributed, okay, within that area. Oh, so that means we know that J is just the total current into the total area. يعني ما يسمى بالتيار النسبي سميت التيار النسبي ايش يسميه؟ عموما يعني انا اقصد انه ايش بالعربي يكون كثافه. نعم، التيار ذو الكثافه J، هذه معناته الكثافه، فالكثافه معناته تيار على اريا. اوكي، هذا هي المقصود. طبعا انتم تيجي عارفين انه هذا، لكن because this is uniformly distributed فهذا معناته انا I am not looking for the total I am not looking for the all total I am looking to the current within this loop here, the Amperian's loop اللي انا رسمته هنا. طيب الامبيرينز لوب يقع على جزء فقط محدد من الكوندكتور. It is not with the whole conductor. Okay, so how can we understand the relation, this relation? نقول no problem. In this small fragment, okay, or small cylindrical, خلينا نسميه the cylinder small داخل السلندر الكبير. Okay, actually we have a small current Let's call it I small. Okay. And this one actually it covers a small area. Let's call it A small. Okay. And because J is uniformly distributed within that area, معناته إنه I capital over A capital equals to I small that I'm looking for. أنا أبحث عن هذا شباب عن I small and the current which is enclosed by the Amperian's loop. Okay. Divided by A, which A is this one actually. This is the shaded area here. هذه الحين الاريا اللي انا عملت لها shading هذه هي اللي مهمه بالنسبه لي. Why is that? Because it is enclosed by the Amperian's loop. From here, I am looking for small I. Okay, I small I equals to يا شباب على طول A small over A capital into I. Do we have the I, the capital I? Yes, it has been given here as a 50 ampere. Okay. Do I have A small? Yes, I can get it A small because A small is the area of the shaded area here. So A small is represent the shading area. Oh, so I have two circles here, the Amperian's loop circle and the smallest circle here. If I subtract the bigger one from the smallest one, so then I can get it. I can actually write it here. يعني I can write it here. The area of the small one in general يعني. Okay. هي عبارة عن ايش يا شباب؟ عبارة عن باي. We know that this is R square, but because we have the R here, the biggest R, okay, let's call it, in this case, it is 4 centimeter square minus by R, which is in this case, it should be the smallest one, which is here, the red color here, the smaller one here. So this will be the square, okay? And then for the largest one, it will be also the same thing. But the largest one is what? Is between the large one here outside, here, this one, okay? This one, and the smallest one, which is this one, okay? So in this case, it will be by the largest diameter, 5 squared, minus by, and this will be, again, 3 centimeters. Okay. So I know the smallest area, and I know the largest area. So what I should do here, I just make them, and then, I mean, apply them in that equation. So small I just will be like by like 16 minus 9, okay, divided by pi. Again, we have here 25 minus 9. And this is multiplied by I. And we know I is just 50 ampere. So what I should write here in I enclosed. Okay, so I enclosed equals to يا شباب ايش؟ By will go with by 16 minus 9 is just يا شباب 7, yes, divided by 25 minus 9, that will be 16, okay, into I, which is 50. So this is actually the I enclosed that I should take care about, okay? It's not the whole current, it is the current that's moving in that portion, that small area surrounding by the Amperian's loop. Okay, so this will be like 7 over 16. And why I shouldn't take care about the centimeter cube, centimeter squared there, because it will be on the top and down, it will go. And that will be very easy to me. I mean, it's not that difficult. But what I should take care about is this one here. So to the left side, I have here R. So, and R, it's 4 centimeter. So I should take care about that one, okay? So then B now it's very easy. We have everything here. Okay. By it can go with by 4 with 2, then we left with 2. So we have 2 into 10 to minus 7, 7 over 16 into 50, and then we have here R, which is 4 into 10 to minus 2. Okay, and you should get B if you calculate it very good here, very well. I think it is 1.09. Okay. 10 to minus 4, okay. So this is the part B. You check it out, please, and find is it exactly the same like this one. So it's 1.0, okay. Okay, so this is the part B. So now we understand how can we get the current that we are interested in. Okay, it's not the total current because we should look for only that area. Part C now, we should look for R beyond that, okay, which is 6 centimeters. So we have the third situation. Okay, let's take these out now. Okay, now we have to look for the third situation. In our third situation here, first let's draw it. So now we are looking for Amperian's loop, okay, which is outside here. So our Amperian's loop will be outside, okay, the conductor here, because now this is the origin. So this is 6 centimeters. Okay? We know that this is 5 and this is 3. Okay? Again, it's the same game, but in this case, Shabab, the Amperian's loop here, this one, the Amperian's loop, let's call it like that, now covers the whole conductor. So in this case, it will be very easy for us. We know that in part C, we know that this is the integral of P to dl, and the left side is very easy for us, equals to mu naught I enclosed. What is I enclosed now? Actually, it's the total current, okay, in that conductor. And sometimes people, they are writing that one actually as J into A, and that's the same thing, okay? But in our case, it is and هذا اثنين J into A equals to the current, actually, the total current. Okay. So this will be mu naught into 50, okay? And here it's again B into 2 by R, and don't forget R equals to 6 centimeters. From here, you can calculate that when B, it will be like, I think it's easy for you, mu naught to 50 divided by 2 by, and this is 6, 10 to minus 2. Don't forget minus 2. The conversion is important because your result will be different if you didn't take care of that one. Okay?